So, we learnt elastic rheology, and now we will switch to viscous rheology. For elastic rheology, we have seen that the strain is recoverable if you remove the stress. And interestingly, there are many materials, many natural materials that we see every day. This process do not happen, that if you deform something, the deformation remains. At the same time, you have seen that flow of water or flow of water with some sediments, and then magma flows and things like that. These things are not likely to be elastic. So, you need a different kind of rheology or another rheology which is not similar to elastic rheology, and therefore, we introduce this term viscous rheology, and this is what we are going to learn now. So, as I was talking about, the way the rocks behave under stress on the surface may not behave in a similar way at greater depth, where you have much higher pressure and temperature, and rocks are not really a solid material there. So, you can think of the example of the glass that we have cited in the very beginning, that at surface temperature it is extremely brittle, it produces fracture, but when we heat it up, it flows like honey. So, in a very similar behavior we can observe in rocks at greater depth. So, we need a different kind of rheology which we actually can apply for hot rocks. And in this case, when you apply a diuretic stress to these hot rocks, or we can consider this now as a fluid or a fluid like material, the first instance it reacts the way that it has a resistance to response to the stress you have applied, but it tends to flow in response to the stress. Now, when the stress is removed, the flow stops certainly, but this material or the deformed fluid does not come back to its original position. So, their shape and their geometry etc., remain permanently to their deformed state. So, therefore, the deformation in this kind of under this kind of rheology is permanent and non-recoverable. And we will also see that the flow rate, or the way we explain flow rate, is how fast or how slow it flows or it deforms. Say for example, if you just put water along a slope, it flows very fast, but if you put honey under the same slope with the same under the same gravity load, it does not flow as fast as water flows. So, water has a higher flow rate and honey has a lower flow rate. So, this flow rate in general of this fluid is also a function of applied stress, and we will see that as well. Now, how to visualize this viscous rheology? The best way, or to visualize it like we saw for elastic rheology, it was a spring, and this time it is a dashpot filled with a fluid. What is dashpot? Dashpot is something that we use in our door stopper, like you open the door and then you do not want the door to close very quickly. So, you want the door to close very slowly, and then there you have a device at the top of the door with a little barrel, and this barrel actually is a dashpot. So, what is inside the dashpot? Let us have a look. So, the first diagram what we see here, so it is a barrel or a cylinder where it is filled by a fluid, and then you have a piston inside. So, this is the cylinder. So, we are looking at a cross section. This is the cylinder, and then we have a piston. Piston is like a T-shaped material, and the top part of the T or the piston is porous. So, that means this fluid filled cylinder, in this case the fluid is the blue color you see here, they can flow through this piston, and the flow must happen if there is any differential stress or pressure. Now, this is a simple piston dashpot or some sort of piston cylinder. Now, the way the viscous rheology is explained using this dashpot is that, So, at T1 time, here is T1, it stays in its stationary mode, and then you can apply an instantaneous load to this piston. So, which are represented by these 3 green bars or 3 green loads. Now, when you apply this load to this piston, unlike the elastic materials, it does not deform the fluid, or the piston does not come down immediately. So, I keep this load constant, and then I see this piston is slowly moving down. This is how it happens, and you can see that the load is constant in all stages. So, the response is not instantaneous, but it happens very slowly. And interestingly, for this material, we see that the response, or what is given in this diagram, that this increase of the deformation or the elongation is linear. Now, at T6, after T6, we remove the load, and interestingly, unlike the elastic materials, this piston does not go back to its original position, it remains there. And this entire behavior of the deformation is known as viscous deformation, where in nutshell that the material does not respond immediately after application the stress, but it responds slowly, and the response, at least in this case, is linear, and when you remove the stress or remove the load, then it does not come back to its original position, and this is known as viscous rheology. Now, you can clearly understand that instead of 3 green bars, if I would have applied 4 or 5, then probably the movement would be faster. Therefore, the greater the load applied, the faster the fluid percolates through this porous spaces of this piston. Now, we can visualize these in terms of plots. So, what I have here, like we have seen in elastic materials, in this area, in this plot I have sigma xx, that means the movement along the x direction. So, this is x, and then this side I have time. So, this is the time, and here instead of sigma I have strain. So, how strain is responding with time is shown here, and how stress is responding with time is shown here, where the time is corresponding to each other. So, what is happening at T1 time, it was there was no load. So, stress is 0, strain is 0, which is normal, which is expected. And now, an instantaneous load has been applied, this 4 bars, and we see that strain here is not instantaneous, but it is increasing slowly. So, you applied the load and kept it for a while. So, here during the application of the load and when we kept the load at constant value, the strain increased, and when we reduced the load, it did not come back, but it stayed at a constant position. Therefore, this is the permanent deformation of this fluid. Now, we can also understand that instead of, say, whatever fluid you have used, say cooking oil, if we use some other fluids like honey, then under the application of the same load, the flow would be slower, and if we heat the cooking oil and put it inside the cylinder, then the flow would be faster. So, of course, in all cases the load is unchanged. So, therefore, it has some response or some relations with some sort of ambience, what is the material, and at the same time some external parameters, influence of temperature and so on, as we have seen with the glasses. We will learn about it later, that what are the influences of the external parameters to all sorts of rheology, but this is in nutshell what is viscous rheology, that we can understand very easily and very quickly with the example of a dashpot. So, as we have learned that fluids in general has a resistance to flow under stress, and this typical term, that resistance to flow, when you try to quantify this resistance of flow of fluid under the application of stress, is known as viscosity, and viscosity is generally denoted by the Greek letter eta, or sometimes we call it coefficient of viscosity. Now, greater the viscosity value, higher is the resistance to flow. So, honey is a high viscous material compared to water. So, you can explain this way. So, when you say viscosity is high, that means it has higher resistance to flow. And if the viscosity or the viscous material that we are considering is a perfect or ideal viscous material that we hardly see in nature, then it flows like a fluid when influenced by an external force. This we have learnt, and that means that there was no elastic deformation involved. So, if we then plot the stress versus strain of the deformation of this ideal viscous fluid, then we would not have any elastic deformation. So, in this side, in this plot, I have along vertical axis stress and horizontal axis strain, and we see that there is no elastic deformation. So, you apply the stress and there is no elastic deformation, and then you have a permanent strain for a constant strain rate. However, because this is rate dependent, the deformation, that means it takes some time to respond and it flows with time under the constant load. So, strain rate here with the viscous rheology is very important, and then if I plot stress versus strain rate, then the plot actually looks like stress versus strain plot of elastic deformation. In elastic deformation, stress versus strain was linear, and in this case stress versus strain rate is linear. So, if I plot stress in this side and strain rate along the horizontal direction, then I get a curve like this for an ideal viscous material. Now, when this deformation of ideal viscous material happens in constant volume, then we call it linear viscous material, or sometimes or most of the time we actually refer it as a Newtonian fluid or Newtonian flow, and the constitutive equation in one dimension actually therefore relates, because we have to relate the strain rate. So, for a normal diuretic stress component, if we use the normal stress, then it is related to the normal diuretic stress component, which will refer as sigma dn, to the instantaneous extension rate, which is epsilon dot n. Now, epsilon dot n, again this dot always indicate epsilon dot means epsilon by t, right. So, where t is the time, or you can also relate it with the shear stress. Therefore, you can assign shear stress as tau, as we have been doing since the beginning, and the instantaneous shear strain rate. So, the equation then takes the form. So, you can clearly understand from this equation that stress or sigma is proportional to the strain rate, right. So, you need a constant to make this equation. So, we simply write a constant, which is in this case the viscosity, the coefficient of viscosity, and strain rate, and this is exactly the same equation in the same form we are looking at. I am sorry, it is this one and this one. So, we can actually extract viscosity from this equation. So, it takes the shape of like this, and here it takes the shape of like this. Now, viscosity therefore is a term that we have learnt is a constant, is a coefficient, and this is a constant for each material when other parameters are constant, pressure, temperature, and so on. The SI unit, as you can see, that viscosity is actually, so if I look at here, so I have stress, so unit is Pascal, and then I have strain rate. Strain does not have any unit, so strain is unitless or dimensionless, but time has unit second. So, and time comes at the denominator of the denominator. So, it would be Pascal multiplied by second. So, the unit is Pascal dot second, or you can write it kg per meter second power minus 1. And there is also one unit of viscosity that people use frequently, it is Poise. So, Pascal second is the commonly used SI unit, but Poise is another unit, and 1 Poise is 0.1 Pascal second. So, that is the conversion of Poise to Pascal second. Now, you can ask this question that okay, so viscosity we learned, dashpot we learned, linear viscosity, Newtonian fluid we learned the dimension of viscosity, which is Pascal second. Now, what is the implication of viscosity in earth sciences? Now, what is the implication of viscosity in earth sciences or structural geology, the course we are learning? So, you can clearly visualize the fact, to answer you this question, that in a very simple way, say a rock is layered in the scale you are considering, and you can imagine, say as an example, that in very micro scale a layer of quartz and a layer of mica, they are alternated in a mica schist, or in a type of schist where you have mica and quartz as dominant minerals. Or you can think of in a little larger scale, outcrop scale or hand specimen scale, that silicate and carbonate rich layers like we see in calc silicates. Then it is important to visualize the fact that at high pressure temperature, when these minerals or these rocks are like fluid, then quartz layer, because it is quartz, it has different viscosity to that of the mica. And similarly, a silica rich layer would have a different viscosity to that of the carbonate. Now, under that conditions, if I deform this rock by compression or by extension, what are the different kind of structures we can produce? And this is a subject of research since years, and people still are continuing researching on this. Say for example, whether we would have a budinage with sharp fractures, or we would have a pinch and swell structure under the same dynamic condition, is governed by what is the viscosity of the budinaging layers and the surrounding materials. I have some examples here. You can also think of the fact that the thickness of the fold, if you go to the field, we will learn it later, that in few folds the thickness of the hinge zone, the top part of this fold, is thicker relative to its limb, and vice versa, that hinge is very thin compared to its limb. And sometimes we see that throughout the fold the thickness is constant. These are known as parallel folds. So, why these kind of differences we see when we know that buckle folding is just you need a layer parallel compression, but these are all functions of viscosity between the layer we are considering, which is being folded, and its surrounding rock, which must have a different viscosity to produce fold. So, here is one example. For example, this orange layer is embedded in another layer in the matrix, and if this matrix has viscosity eta 1 and the orange layer has viscosity eta 2, then to produce a fold, buckle fold, the eta 1, that means the viscosity of the matrix, must be pretty less than the viscosity of the buckling layer. And if that reverses, that is, the viscosity of the buckling layer is lower than the viscosity of the surrounding rocks, then we would produce a structure something like that. And you can clearly understand that a switch from here to here is only possible not by any dynamic change of any dynamic parameters. That means you are deforming it slowly or you are deforming it very fast, does not matter. You can switch from this to this only and only if you have a viscosity difference between these two in a different way. Very similar way, if the same layer stays in an extension regime, then we can see that we can form sharp fractured budinage when the viscosity of this budinaging layer is very high compared to the viscosity of the surrounding matrix. If it is almost similar or slightly higher, then we can produce some sort of structures that we know as pinch and swell structures. So, what we are dealing here is some sort of relative viscosity, that we are comparing viscosity from one layer to another layer, and this relative viscosity sometimes is referred as competency in structural geology, and we will refer it later as competence contrast. And this is also referred not only for viscous rheology, we also use for elastic rheology, that elastically competent layer, elastically incompetent layer, viscously competent layer and viscously incompetent layers, and so on. So, we will see later many more applications of viscous rheology along with some other rheologies, but to give you a very brief idea that why we need to study rheology to better understand the structures that we see in the field in structural geology, it is very important that we have a solid background of rheology. Now, we talked about linear viscosity. So, and this is evident from this equation where shear stress is equal or proportional to the shear strain rate with a constant. So, this suggests that the viscosity changes linearly with strain rate, and it is only applicable for linear viscous fluids or Newtonian fluids. As an example, you can consider water, magma under certain conditions, flow of salt in salt domes, etc., are fantastic examples of Newtonian fluids. But there are many other flows where the flow do not happen linearly. What I mean by linearly is explained here. So, we have seen this plot, the stress versus strain rate, where the relationship is a straight line. That means at any point of time of the deformation, if I go back to this plot, I always can get a viscosity, and in this case when it is linear viscous fluid or Newtonian fluid, the viscosity is constant. And if that does not happen, then this line is not straight anymore, it can be curved. And if the line is curved, then the relationship is not linear, and this is known as non-Newtonian viscosity or non-Newtonian flow or non-Newtonian fluid. So, what does it imply? That with deformation, if I take any point, draw a tangent and then try to figure out what is the viscosity, you can see that viscosity is constantly changing. So, this changing viscosity or the transient viscosity during deformation, while the all parameters pressure, temperature and others remain constant, this is known as nonlinear viscous fluid or non-Newtonian fluid. So, to figure out a constitutive equation for non-Newtonian fluids, you can clearly understand that this linear equation is of no use. So, we introduce a new kind of equation where strain rate is related to stress with some sort of exponent, and in this case this exponent is n and it is known as stress exponent. In structural geology, in tectonics and also in geodynamics, this stress exponent is a very important term, we will learn about it later. And then this is related by a constant which is material constant, and we generally denote it by A. So, eventually the equation takes the form strain rate equal to a constant multiplied by sigma to powered by an exponent. So, this exponent is known as stress exponent and A is a material constant, and because it has a power, sometimes we refer it as power law flow, or the materials which do not have a linear viscosity property, we call it also power law materials. Now, we move to plastic rheology. We learnt elastic rheology, we learnt viscous rheology. and there are many materials, the behavior of which under stress we cannot explain neither by elastic rheology nor by viscous rheology. So, we need a third and final end member of the rheology group, and this is plastic rheology. So, under some natural conditions, as I was talking about, the strain response of rocks cannot be explained neither by elastic nor by viscous rheology. And these materials are extremely typical. So, during deformation they initially display an elastic behavior, however, after a certain point they flow readily at or little above the yield stress. Now, this is something, a new term we are learning, yield stress. We will talk about it later, we will learn more about it, but for the time being you just know yield stress as a kind of a typical value of stress in deforming a material, or you can consider it as a threshold stress. So, for the timing you just remember that. So, in nutshell, that you need to deform it elastically initially, and then once you reach a typical value of this elastic stress, which we have referred as yield stress, then the materials do flow either at the yield stress or a little above of the yield stress, and this typical behavior of the material under stress is best described by a rheology called plastic rheology. Now, plastic rheology is essentially a description of a material behavior under stress to undergo irreversible or permanent deformation after the yield strength. So, yield strength is something that is the limit of your elasticity. So, that defines now what is yield stress or yield strength, that after you reach the yield stress, then you cross your elastic limit and the elastic property of the material is gone. You cannot bring it back to its original position. Whatever happens after that is elastic deformation. So, during the post-yield deformation, it is very interesting for plastic material, the rocks have to maintain its continuity. That means, I am stretching a rubber band and I cross the threshold value of the elasticity, which is yield stress, and immediately after that the rubber band breaks, then this is not a typical plastic rheology that we consider. The rubber band has to getting stretched, and if I release it, it should not come back to its original position if it is a plastic material, perfect plastic material, but rubber band is not. So, plastic rheology is best explained by a mechanical analog we generally call a friction block, or a, so it is something like a frictional resistance on the sliding of a block on a surface which has some sort of frictional resistance. The explanation is given here with this series of illustrations. So, what happens, this grey shaded platform is, you can consider a table which has rough surface of which has a friction, and then on the top of that we have a block with some hook there. Now, once I rest this block on this surface, that has then this interface of this block and this surface has a friction between these two. Immediately the friction develops immediately when I try to pull this, right. So, it has a friction, and I can actually consider this friction as the yield stress, which is sigma y, right. We have given an example in the beginning that you cannot move anything instantaneously. So, at T0 everything is in rest, and this frictional interface has the frictional resistance value sigma y, or coefficient of friction, which is, in this case we are considering it or some sort of making it analogous to the yield strength. Now, at T1 time I started pulling this block with a force F, and I am not changing the, and I am slowly increasing this force at time t2, between t1 and t2, what is happening? This F has closely reached or slightly above this sigma y value, and once I cross this sigma y value, this block has to move, and as you can see in this image, this block has moved. And if I continue applying this force, the block would continue to move, but at time t4, if I remove the force, the block stays in its original position, it does not come back to where it is. So, it is not essentially, not at all, an elastic deformation. So, if I try to look in a very similar diagram that we have been looking at, where you have stress versus time and strain versus time, the first one is your cause, second one is your effect. What is happening here? When you have no stress, there is no strain, and now you started applying F slowly, but you have the frictional resistance. So, the material is not moving. So, you can see there is no strain even if you have applied a significant amount of stress. Now, when immediately you reach the stress value equal to your yield stress, or in this case the frictional resistance, then the material starts moving. Now, here I have 3 different curves, and this can be, there can be n number of curves. We will talk about it later, but let us consider only one. So, it can then move or it can get deformed because it is changing its position, and then if you release the stress, it does not come back to its original position, right. So, this is in nutshell what is plastic deformation or plastic rheology, using the analogy of a friction block. Now, why we can have some n number of possibilities of different curves? It is simply because when the block starts moving, then you do not have any control to the displacement, right. So, this is some sort of material property which is independent of the force or stress you are applying. So, what is written here, the velocity of the block is 0 till the force equals to the sigma y or yield stress. After that, this is very important, the block can move with possible velocity and not a function of the applied force, and this is why, as the force never exceeds the frictional resistance except during acceleration. So, if you have to accelerate this block, then you can increase the force and then you can have a certain curve, but otherwise it can move to any possible values. So, now if we would like to express the plastic rheology mathematically, then we have to consider an ideal plastic material or ideal plastic rheology. So, which is known as also rigid plastic material or Saint Venant material. So, generally the behavior, the constitutive equation of ideal plastic rheology is expressed with the consideration that there is no strain at all below the yield stress. So, that is a very primary and basic consideration, that material does not deform even elastically till the yield stress is reached. Okay. And at the same time, during the deformation, the stress cannot be above the yield stress except you have acceleration. Now, this is a little complex in terms of statements, but in general you are not accelerating your material while you are deforming it, that is the first. And second, that at the very beginning, before you reach yield stress, there is no elastic deformation, and this relationship is explained by this equation sigma, either that is your overall stress is less than or equal to the yield stress, and this is known as von Mises yield criteria or von Mises failure criterion. And you can expand these part in this form sigma involving all sorts of principal axis of stresses, and if you can recalculate it to your stress slides that we have seen, it is the stress invariant number 2. So, you can figure it out, and we can also figure out the stress does not determine the strain rate, and the equation also does not say anything about the possible values of stress after the yield. So, therefore, you do not know what would be your stress value after the yield, and that gives a very interesting phenomena of rock deformation in structural geology of plastic deformation, and which we are going to see it now. So, we know that rocks are, I mean, whatever we have considered so far, elastic, viscous and plastic, we always use the prefix before them is that ideal, and ideal means it is very difficult to find, to figure out. So, like in all other materials, rocks also are not ideal plastic materials during plastic deformation. So, strain rate and others would like to have an effect, and the stress level is likely to change during the deformation history. And also you may not have no elastic deformation before the yield stress. So, you may have elastic deformation before the yield stress while you are deforming the rock plastically. So, this is mostly visualized by different rock deformation experiments with variable materials at variable conditions, and these experiments revealed the fact that at different experimental conditions there are number of possibilities of plastic behavior after the yield stress. Now, this plot shows that behavior of an ideal plastic material where you do not have any elastic deformation, you straight away reach to the yield stress. When you reach yield stress, your strain remains 0. So, there is no deformation, you straight away go to your yield stress. Once you reach yield stress, then you increase the strain, keeping your stress at more or less on your yield stress value, and if you stay really on yield stress value, then you are dealing with one ideal plastic rheology. But as I said, rocks are not ideal plastic material. So, you generally would expect some sort of linear behavior at the beginning between stress and strain, and therefore, this is your elastic domain, and then you reach your yield stress. Now, post yield deformation, there are several possibilities, and we can categorize it in 4 different ways. Now, if after the deformation, after the yield, I am sorry, after the yield, if the material deforms at a constant stress, what we see here with a green curve is known as steady state flow. If you need some more stress to flow the rock or to deform the rock, then this is called it strain hardening. If we do not need stress, even that much of the yield stress, much lower stress to flow the rock, this is known as softening. We observe all sorts of curves in rock deformation experiments, and together with this we saw curves that involve both hardening, steady state and softening, which is the orange curve here that goes like this. So, you see after the yield you have hardening, then you have softening and then steady state. So, this is known as complex flow or complex plastic rheology. Now, all such processes can be explained by the deformation in atomic scales, that why I should have hardening, why I should have a steady state flow, why I should have a softening type of flow, a strain softening type of flow. Now, these are essentially very micro scale processes, and we will learn it in one of our next lectures, where we will be dealing with deformation mechanisms of rocks. So, with this we finished the 3 basic end members of rheology, which is linear elastic, ideal linear elastic, ideal linear viscous, and ideal plastic. And here is the summary slide. In ideal linear elastic materials, we use spring as our analog model. For linear viscous material, we use a dashpot. For ideal plastic rheology, we use a friction block. The stress strain curve for ideal linear plastic, where stress versus strain is linearly related. For viscous, this curve is little difficult, not linear. It goes like this. For ideal plastic, the curve looks very similar to the linear viscous material, but here this point has to be your yield stress. Now, stress rate versus strain rate plot for ideal linear elastic material is exactly same the way you have stress versus strain, but in linear viscous and linear plastic materials we do not plot stress rate, but we plot stress versus strain rate. In this case this is linear, and in this case this is not linear, but it looks exactly similar of the stress versus strain, because it is strain rate independent if your material is ideally plastic. We also have learnt a lot of terminologies, right? Viscosity, Newtonian fluid, compressibility, Young's modulus, von Mises criteria, then elasticity, strain hardening, and so on. Now, you can see that all these words or phrases that we have learned in this basics of rheology lecture, I have sort of jumbled up. So, what you can do, that you can pick any of these terminologies and can think of, what is this? Say if you just talk about Poisson's ratio, okay, what is Poisson's ratio? Let us think about it. If you do not get it, go back and look at what is Poisson's ratio. This is how you will be very familiar with these sort of terminologies, which are extremely important to understand the deformation of rocks at different conditions. So, with this we finish this lecture. In the next lecture we will learn the combined or complex rheology, where we will add one basic rheology to another basic rheology, and we will see what kind of responses we get out of it. Till then, goodbye.